Hi, so it's nice to be back once again at the Institute. I was a student twice at PITP, so it's kind of fun to be on this side of the lecture hall this time. I had a great time both times, so I hope you're all enjoying yourselves. The general question that I want to discuss today and tomorrow is how does space-time emerge? So that sounds important, and like most important questions, I'm not really going to be able to answer it. So I'll immediately start qualifying it. So we'll begin by qualifying it within ADS CFT.
Try to write a bit larger.
All right, it's already too small. Okay. All right. Okay, I will try to. Okay, so how does space-time emerge in ADS CFT? All right, now we're getting a little bit more concrete. But maybe still that sounds a bit vague, so let me try to ask a more concrete question. So is there a black hole interior in ADS CFT? Okay. Ahmed in his lectures gave some arguments that maybe the answer is no, or maybe it's yes in some states, but not in typical states. And if we can't answer that question, then it means we don't understand ADS CFT, right? We're told ADS CFT is a theory of quantum gravity. And so anytime someone comes to you with a theory of quantum gravity, you should ask them, okay, how do you describe the black hole interior? And if they can't answer, then it means they don't really have a theory of quantum gravity, or at least if they have it, they don't understand it yet. And so this is a question that I really want to understand. And then we could be ambitious, and we could ask for general lessons for other spacetimes. So, having exhausted ADS CFT, then we can try to move on to more realistic situations like de Sitter space. So unlike what you heard in the news, we probably still live in de Sitter space. But these problems, of course, I'm also not going to solve today, because if I did, I would be going to write a paper about it instead of talking to you guys. I would say, though, that in the last, let's say 5 years or so, there has been, I would say, quite a bit of partial progress towards understanding these questions, and that's what I'm going to try to explain to you. So concretely, there's a question of how to represent bulk operators in the CFT. So that's a question we could ask. You have some operator in the middle of the bulk. How do you think about that in the CFT? We'll talk about toy models of the emergent radial direction. We'll talk about an improved understanding of the Ryu-Takanagi formula. Let's see if I can figure this out. Less inertia than I thought. And then finally, we'll discuss proof of what's called the entanglement wedge reconstruction, which tells us that at least in some situations, ADS CFT can see into the black hole interior. And so hopefully from this, at least we'll be able to eventually understand just how general those situations are. And in the end, right, if there's some firewall or whatever, right, I mean, we should be able to compute it, right? There should be some calculation we do in the CFT, and when we finish the calculation, it says firewall yes or no in whichever state you give us. And that's at least in this program, sort of the ultimate goal is to think about how one might set up such a calculation, even though we're not going to succeed. So now all of these results come from a new sort of picture of the ADS-CFT correspondence, where we interpret it as a quantum error correcting code. So we'll study these using quantum error correction. And so for us, that's a tool. You know, when you have a hard problem, you want to find new tools, and quantum error correction is a tool. And it turns out that it's going to be useful, I think, at least for thinking about these questions. OK. So now let's just do a little bit of ADS-CFT 101, just make sure we're all on the same page. Not everyone thinks about the correspondence in the same way. Well, damned if you do, damned if you don't. OK. So to me, what ADS-CFT says is that quantum gravity in asymptotically anti-de Sitter space is defined as CFT on R times SD minus 1. And this is ADS D plus 1 here, asymptotically ADS D plus 1. So it says that, well, so sometimes people call it ADS, but of course, if all you really had was ADS, it would be a very boring quantum gravity theory. You would just have the vacuum, and that's it, right? So to get anything interesting, you want to have asymptotically ADS, so you can have excitations above the vacuum. So then it's saying that that's somehow defined in terms of this conformal field theory living on the boundary of the space. And so we can draw the picture where, so on this side we have the ADS side, so there's some radial direction and time going up, and then some angular coordinates going around here. And then this is supposed to be the same thing as the conformal field theory that's just living on the boundary of the cylinder. And in particular, the asymptotic symmetry SOD, 2 of the ADS is the same group as the conformal symmetry SOD, 2 of the conformal field theory. Now, you could ask, OK, it's fine to write this equals sign, but what does it really mean? You know, what's the meat of the correspondence? So we can start at a sort of formal level, and we can just imagine that we have a map, phi, from the Hilbert space of asymptotically ADS quantum gravity to the Hilbert space of the CFT, which is an isomorphism. So for any state in the quantum gravity, we have a state in the CFT, and vice versa. And moreover, we have these nice symmetries on both sides. And so we can ask that the symmetries, I guess the technical term is intertwine with this map in a nice way. So, sorry, U CFT phi. So the Hilbert space is living in the same representation of the symmetry. And actually, from now on, this phi, although in principle it should be there, it's kind of tedious to keep track of. So from now on, I'm going to pick bases so that phi is the identity, and then I'll just talk about everything in the CFT Hilbert space. Now, if I just come to you with a CFT, I don't know, the Ising model or something, then there's actually not too much more that we can say than this, because yeah, you can say the Ising model is quantum gravity in asymptotically anti-de Sitter space, but it's not very realistic quantum gravity in asymptotically anti-de Sitter space. So there's not too much that we can say about it. What was their question? Yeah.
Is there a significance of the way unit rings have been composed with the states in that equation?
Sorry, what?
On the ADS side, we have the symmetry on the acting on the right, and on the CFT side, we have it acting on the left.
Yeah, did I get it wrong?
No, is there a significance behind
Oh, U is a unitary. So like in any symmetry in quantum mechanics, it's represented unitarily on the Hilbert space. So this is a unitary operator here. So then the rule is if I act with the unitary operator here and then do the map, I get the same thing as if I act with the map first to go to the CFT and then act with the symmetry there. Yeah. Intertwining, I think. Okay. So to put some meat on this, we have to talk about those special CFTs where the quantum gravity that they're dual to is some quantum gravity that is in some sense semi-classical, something like the gravity that we actually see in our world. And so we can put a restriction on CFTs. We can say we're only going to be interested in those CFTs which have the special property that, let me write it this way, that there are some low-dimension primary operators where if we look at their correlation functions, Tn omega n, in the CFT, that it's actually equal to what we would have gotten from some bulk path integral with some local effective action In, oh god, this is long, omega In, where in particular you can ask, so here these are CFT operators. I put the same things here in the bulk path integral, so you have to ask what those are. And so what those are is given by this so-called extrapolate dictionary, which says that OI of T and omega is equal to the limit as r goes to infinity, r to the delta phi I of r, t, and omega. And we'll have to use this equation again, so I'll put a box around it, and I'll give it a name. I'll call it equation smiley face. Okay. So not all CFTs are going to have this property that there's some bulk effective action such that the correlation functions of the fields in that bulk effective action are equal to the correlation functions of the CFT. And then I want to emphasize this is supposed to be true sort of to all orders in 1 over lambda. So plus corrections, which we might think of as something like e to the minus lambda. Okay? And now let me emphasize that in order for this to make any sense, what I need is that lambda is large in ADS units and small in Planck units. Okay. And so in some sense, you know, people sometimes talk about, can you prove ADS CFT? Well, you know, it's kind of hard without having an independent theory of quantum gravity here. But one thing you can ask is just, are there CFTs which have this property? That's at least some non-trivial statement, right? It's not obvious that there are CFTs where there's some bulk path integral that spits out the same correlation functions to all orders in 1 over lambda. So to the extent that's true, ADS CFT is a non-trivial statement even without having an independent definition of quantum gravity. Okay. Now, indeed, it's an interesting general question which CFTs are the ones that have this property. And in general, it's a hard question. We don't know. There are some conditions in the literature which are expected to sort of be sufficient. You know, so people sometimes say things about having a large gap and having a large n limit and so on. And all the fine print is not so clear in those words. Yeah, in general, I would say that we don't really know what is the necessary and sufficient condition, either a necessary or a sufficient condition. Now, I also just want to comment. So I've already actually, the way I said it here, we actually don't know any examples because I didn't put asymptotically ADS times something, right? So in the examples like n equals 4 super Yang Mills, you have ADS times S5, right? Or you can have ADS 4 times S7. And as far as I know, although maybe someone can correct me, in all the examples where we actually know the CFT, there's always this big manifold there. And I've neglected that in what I said here, and I'm going to continue neglecting it. But I don't think it's a capital crime, because in string theory, we certainly formally know how to construct examples where all the compact directions are small. You know, you can just have some Calabi-Yau with some flux or something. It just doesn't have enough supersymmetry that we can tell you exactly what the CFT is. Okay, so I will continue neglecting the M, but let me just comment that had I not neglected the M, then it actually would not be true that each field in the bulk corresponds to one operator in the CFT. Rather, each field in the bulk would correspond to a tower of operators in the CFT, having to do with at what point on the S5 you approach the boundary. And so to not deal with that, I'm just never going to discuss this S5 type thing. All right. So actually, okay, I can move it up later. Okay. So this set of rules, it's simple, but it's actually already pretty good. It lets us, at least in principle, compute a lot of stuff. So in particular, any experiment in ADS that we can phrase as a scattering experiment. So, you know, for example, we send in some particles here and some particles here, and then there's some interaction, and then some particles come out. Well, we can rephrase that in terms of some correlation function in the CFT by using the extrapolate dictionary. And this can be a rather complicated scattering experiment, right? Like these guys could have enough energy that they collapse to form a black hole, and then this could be the Hawking radiation, right? And we're just trying to, we can just read that off of these correlation functions of primary operators using the extrapolate dictionary. But this is not enough for every experiment that we could possibly imagine wanting to know the answer to. And in particular, so here's one. So here I'm drawing the Penrose diagram of the thermofield double. So here's the bifurcate horizons. Okay. So we can send in some particles, say from the two sides, and they can interact in here. And now some stuff will come out of the scattering experiment, but it never makes it back out to the boundary because it just goes into the singularity up here. So I actually don't know how to measure, you know, compute, say, this S matrix element using ADS CFT because I don't know how to talk about this final state in the CFT. Is there a question? Well, yeah. So in ADS CFT, sort of spatial infinity is all there is. But yes. So you could imagine, for example, I prepare some initial state on this slice by acting on the thermofield double with two operators here and here on the two opposite sides. I don't need to have the two sides. We can have one black hole and go from opposite directions. It's easier to draw the picture if I use two asymptotic boundaries. Yeah.
Why don't you consider the geometry beyond the singularity? Because in Rindler, near horizon, Rindler and Nostrom, there is geometry beyond the singularity.
The geometry beyond the singularity. Well, here I'm considering a Schwarzschild black hole, so I don't think there's any geometry beyond the singularity. I mean, we could discuss, but if somehow there is geometry behind the singularity, my statement is still true. I don't know how to phrase that in terms of these correlation functions. Yeah, I mean, I guess if I had to bet, I would say there isn't any behind it. Yes?
But if you wait long enough until it evaporates, this black hole, but you will be able to see.
Yeah, but that's not asking this question, right? So I want to know, you know, if I'm sitting up here, right, what's the probability that I see such and such decay products coming out of this? If we wait until it evaporates, it's more like this question, where I'm talking about stuff coming out in the Hawking radiation. And we can fantasize that there's some map between the two, but I don't know, you know, at the level of the extrapolate dictionary, I have no idea what it is. Yeah.
Do we think that eternal black holes are generic states in ADS CFT, or do we think that like collapsing and evaporating black holes are generic states in ADS CFT?
Well, I certainly don't think the thermofield double is a generic state of the two-sided system.
But we think it's representative, right?
I actually don't. I think too much attention is paid to the thermofield double, including by me, so guilty as charged. It's so nice to think about. It's hard not to. But, yeah. Okay. So somehow, if we want to answer this kind of question, we need more than just the extrapolate dictionary, and that's what all these lectures are going to be about, is what that more is. Okay, now I need the stick again. All the way up. I'm going to kill myself if I don't. All right, so now I'm going to talk about this idea of bulk reconstruction. So the goal of bulk reconstruction is to find a CFT representation as an operator, not just of these limiting things that appear in the extrapolate dictionary, but this phi of r, t, and omega when it's sitting at a finite point in the bulk, right? Because remember, I told you that the correspondence was an isomorphism between Hilbert spaces, so every operator on one Hilbert space should be mapped to an operator on the other Hilbert space, and we just need to figure out which operator it is. Now, there are two things that you can complain about. And probably some of you are already silently, or even to your neighbors, complaining about them already with this idea of finding a CFT representation of phi, r, t, and omega. So let's deal with them right up front. So complaints. Okay, so the first complaint is that phi of r, t, and omega is not diff invariant. Okay, and that's true. So phi of r and t and omega doesn't make any sense. So what am I trying to do? Well, that's a fair question. But it's not a serious problem, because we can just essentially deal with it either by gauge fixing or by what's called gravitational dressing, where instead of talking about r, t, and omega as coordinates, we just have to define them in some geometric way relative to the boundary. Now, dealing with that, so every argument that I give below can be made including the gravitational dressing, but it's annoying. So I'm not going to explicitly talk about it. And so at various times I'll be talking about local operators, and I never really mean local operators. I mean gravitationally dressed local operators. But at least as far as I know so far, none of the arguments I say are wrong. You just have to add a little bit of subtext each time. Oh, and by the way, I should have said this in the beginning. So a fair bit of what I say, maybe like 70%, is going to be fairly similar to what's in my TOSI lecture notes, which are posted online. So, and many of the details, like the cross M and the dressing and so on, are discussed in more detail there. But just because I guess some order 1 fraction of you are also at TOSI, I'll try to throw in a few new things too. Yes?
In the bulk, there is a degeneracy in dressing.
Yeah, that's right. And so you have to say which one you mean.
What does that correspond to the boundary?
Well, it's different operators. So if we were to do this at a higher level of detail, when I tell you what the operator is, I have to tell you how I dress it. And until I tell you that, it's pointless to try to reproduce it in the CFT. And there'll be different reproductions for operators that are dressed in a different way. And yeah, I said reproduction, but the standard word is reconstruction. I don't really understand this word, why it's called reconstruction. I guess it's like recombination in the CMB also, where there's some, it was never combined in the first, I don't know. Okay, but anyway, that's what it's called. So reconstruction means you take a bulk operator and you try to find its CFT representation. And I think we're stuck with the name now. I couldn't stop saying it even if I tried. Okay, so this is an obstruction, but it's not too bad. A more serious obstruction is that, well, we know, say from Aaron's lectures, that S is equal to A over 4G. And what that tells us is that the bulk is not local. And that's true. So the bulk is not really a theory based on a local path integral. And so even the diffeomorphism invariant versions of these operators clearly aren't really going to make completely precise sense. Just one sec. They're going to have to be approximate notions which come with both a regime of validity, and even in that regime of validity, we don't necessarily expect them to be completely well defined. So for example, we just have to live with errors that are, say, at least of order e to the minus 1 over g in everything that we do with these operators. And we'll see that actually that's not enough. So moreover, we need to restrict the domains of the operators to a regime where they make sense. And that we'll do a lot of that as the lecture goes on. Yes?
I'm sorry, this is probably stupid, but could you explain your intuition for the arrow again?
The arrow. Oh, well, that's this idea of holography, right? Like if you try to ask how much stuff you can cram into a region of some size, it's not as much as you thought, because before you get to a volume's worth of degrees of freedom, you make a black hole, and then the microstates only grow with the area. Yeah. So somehow that, the whole point of ADS-CFT is it incorporates that, and so somehow this idea of reconstructing bulk operators is going to have to be consistent with that. But let me add that, you could also say that about our real world, and effective field theory seems to hold to a very good approximation around us. So it's a serious, we do have to somehow make sense of this. We can't just plead that it's holography and therefore it doesn't make sense. Yeah, another question?
So the first point, so right, you can easily define it invariantly, but don't you assume here that the topology is fixed, what you should allow to fluctuate?
No, not necessarily. So okay, my favorite dressing, actually not my favorite, but the one which I'll say, is one where you just pick a point on the boundary and you shoot a space-like geodesic into the bulk for a fixed renormalized distance, and then you stick the operator at the end of it. And you can do that regardless of the topology. The key thing is to kind of start at the boundary. And that's, by the way, that's why de Sitter space is so hard. There's no boundary to start from. Yes?
So I don't understand why you need that second bullet point. Doesn't different variance already imply that you can't have multiple operators?
No, yeah, but this is worse than that. So this kind of says that even, so this, if you're willing, so in quantum electrodynamics, right? If you're willing to throw into the Hilbert space some extra states which aren't gauge invariant, you can basically just say, that you have a gauge field at each point and so on. And we can say that in terms of saying there's some bulk path integral with a local Lagrangian, okay? But this is saying there's not even going to be that. So even after you try to somehow take into account diffeomorphism and variance, the theory's got to be even more non-local than that. Yeah, there's some people who somehow think all this follows from diffeomorphism and variance, but I think they're wrong. Okay, any other questions? What? Right bigger, okay, yeah, sorry. Yeah. I'm just lazy about not wanting to. All right, I'll try. Okay, so having now addressed the complaints, or promised that we'll address this one later, we'll start trying to do bulk reconstruction. And so there's kind of a dumb way to do bulk reconstruction, the sort of simplistic thing, which is that you just say, well, okay, I've got the extrapolate dictionary, which tells me what phi is at the boundary on a codimension 1 surface. And when I was an undergraduate, I learned about solving partial differential equations. And one thing I learned is that if you have something that obeys a partial differential equation, then if I give you initial data on a codimension 1 surface, then you can just solve the equation. That's all you need, and then you can find the solution everywhere. Right? So we can say that phi obeys some equation of motion in the bulk, eventually coupling it together with the other fields. And by using the extrapolate dictionary and just solving that equation inwards as an operator equation, then we can get an operator representation of phi anywhere in the bulk. Okay? So let's see how that works just in the in a very simple case. Of Poincare ADS for a scalar field in the vacuum. All right, so write bigger, I'll try. So the metric dxd squared over z squared. So to be clear, this is the Lorentzian dx squared. And so this shaded region here is the Poincare patch. So this is z equals infinity here, and this is also z equals infinity here, and this is z equals 0 all on this region here. And so we learn, I guess in our first quantum field theory class, that if you have a free scalar field in this geometry, then you can represent it as a Heisenberg picture operator, phi of z and x, as the integral ddk over 2 pi to the d, theta of minus k squared. So k squared is restricted to be time-like. Then there's e to the I k dot x. There's some radial wave function psi k of z. And then there's some creation annihilation operators. Where, to be clear, my dk includes both frequency and momentum. So when I write this, my ak could be either a creation or annihilation operator, depending on whether the frequency is positive or negative. Okay. So this is what you get by just solving the wave equation in the Poincare patch. And in particular, this psi k is proportional to some Bessel function. So it's z to the d over 2 times Bessel of 1/2 square root d squared plus 4m squared of square root of minus k squared z. Okay. And this restriction that k has to be time-like comes from the requiring that this psi wave function is normalizable at the Poincare horizon at z equals infinity. Because you want this Bessel function oscillates if this is time-like, but it grows exponentially if it's space-like, and that's not normalizable. Okay, so that's something hopefully you all have seen at some point in your classes. Now, from the point of view of the extrapolate dictionary, the only thing that matters is that this psi k has the property that as z goes to 0, well, there's some constant that depends on k squared, and then it goes like z to the delta, where this delta is d over 2 plus 1/2 square root of d squared plus 4m squared. Okay. So that means that when we take this field phi and we stick it into the right-hand side of the extrapolate dictionary, now remembering that r is 1 over z, so it should be a z to the minus delta, then that just strips off this factor, and we find that in the CFT, O of x is integral dk over 2 pi to the d. Again, we have this theta of minus k squared. This n k squared, e to the I kx, ak. So that's some representation of the boundary operator, boundary CFT operator. This O, remember, is the thing that appeared in the extrapolate dictionary. In terms of the creation and annihilation operators for the bulk field. And of course, the point is that we can invert this by using the boundary Fourier transform. So this tells us that AK is the inverse of nk squared times the boundary operator in momentum space. Finally, we can now just take this expression for AK, substitute it. Let me make a line here to make the separation between these two more clear. Substitute it in here, and we can get an expression for the bulk field everywhere in terms of the CFT operators. And in particular, what we find is that phi of z and x is equal to an integral dx prime, some function k of z and x, and also x prime, O of x prime. And this k is expressed in terms of the modes. So you just substitute this in here, and then you exchange the order of the k integral and the position space integral in this Fourier transform. And that gives you some expression for k, which is called the smearing function. And so here you see we have it. We have a bulk field at any point in ADS, represented in terms of an integral of a c-number function times an operator in the CFT. And so this is an operator equation, giving us a CFT representation of that field. gotta push harder.
So the non-locality is manifested in the method.
Yeah, so this equation is clearly non-local. I was about to comment on that, yeah. So just one sec. Okay. Yeah, okay, so let me first make actually one other comment. Let's see, where did I put this? Oh yeah, I see, okay. Good. So the first comment I want to make indeed is that, so let's look at what this looks like from the point of view of the boundary. So this integral over dx prime is an integral over the boundary of the Poincaré patch. So if we unwrap the cylinder, like that, then this region is something like this. It's this causal diamond of a single boundary time slice. And in fact, so you see that since the operators that appear on the right there, they're always local at some time. But if you try to represent them all at t equals 0 by representing them, say, in the Schrodinger picture, well, then as Douglas was explaining in his talk, right, an operator up here, if I evolve it backwards in time, it grows into a more and more complicated operator. And here we're relativistic, so it grows on the light cone, the ordinary light cone. But it evolves to some non-local mess here. And so you see we have up here an integral over various non-local messes of differing severity. So you wouldn't want to use this operator in the Schrodinger picture at t equals 0, probably, unless you were very smart. Okay, so that's one comment. Another comment is that you can see already that there's a bit of freedom in this representation. Because I said the Poincaré patch, but you could have asked which Poincaré patch, right? There's nothing special about this Poincaré patch. For example, I could act with the rotation and move it around like that. And by doing so, I get a different, or at least seems different, representation of this bulk operator, but it's the same bulk operator. So that's a little bit interesting. And we're going to see a lot more of that kind of thing soon. Right now, it's sort of, when you collapse them all down to t equals 0, it's always some big non-local mess. So it's not that surprising that one big non-local mess looks like another big non-local mess that fills all of space. But at least in that representation, they look different. Yeah? Sorry, what?
Is K the bulk boundary propagator?
No, K is not the bulk to boundary propagator. Yeah, it's important that it's not. Yeah, I don't want to go through and do the Fourier transform to write the formula for it. It's in the notes. But for one thing, the fall off as you move the bulk point to the boundary is different than it would have been in the bulk to boundary propagator. Okay, and so the other comment I wanted to make is that, so for here I just did a free scalar, and so it seems kind of trivial. In some sense, this formula is determined by conformal invariance. So to really get something non-trivial, you have to include interactions. And maybe I'll make a pedagogical comment that in a lot of the literature on this subject, people give proposals which are determined entirely by conformal invariance, and you should never believe those people. Because it's clear that there's more to conformal invariance once you include interactions. So using this method, you can include interactions. You just perturbatively solve the equations of motion order by order in the interactions. And so I explain how to do that in the notes. There's a sort of diagrammatics associated to it, but again, I'm going to skip it, partly because I explained it in TOSI and partly because it's in the notes. Yeah?
So bulk reconstruction in Euclidean is a trivial question?
Yeah, well, I don't know what it would mean to talk about reconstruction in Euclidean space, because I'm talking about operators on Hilbert space. So, yeah. Yeah, so who was it? I think it was Aaron or somebody said that what Euclidean space is good for is a tool for preparing states. Yeah. Yeah.
So is there a way to get the bulk metric in the first place?
Yeah. So I did the scalar for simplicity, but we could also talk about the metric. So that obeys the extrapolate dictionary with the energy momentum tensor. And so we could play the same game. We could solve in this order, it would be the free graviton equation in the bulk. And then we would get some formula for the bulk metric in some gauge, so that's related to this first point. in terms of some integral of the boundary energy momentum tensor against one of these smearing functions. And the gauge dependence would go into which smearing function we ended up with. Yeah, any other questions? Okay. Now, one of the interesting parts of this reconstruction business is that, well, we already saw, even in the Poincare patch, that the reconstruction was a little bit non-unique because we can change which Poincare patch we're talking about. But actually, that's just kind of the tip of the iceberg. And actually, there are many different representations of any bulk field. And in particular, there's one which is very nice, which is called the ADS Rindler well, I should say reconstruction. I always get confused about these terms. So let me remind you how that works. So the basic idea is that, well, the Poincare patch is one nice subregion of ADS, but there's another nice subregion where we take a bulk time slice at t equals 0 and we cut it in half, and then we look in the bulk at its domain of dependence. So that defines some sort of wedge region here. And there are nice coordinates in this wedge where you say that ds squared is equal to minus rho squared minus 1 d tau squared plus d rho squared over rho squared minus 1 plus rho squared dh d minus 1 squared, where this is the metric on the hyperbolic d minus 1 plane, the Euclidean hyperbolic d minus 1 plane. And so in these coordinates, rho equals 1 is up here and down here. So it's kind of like the Poincare horizon. And rho equals infinity is out here. But you see now we don't get a full time slice of the bulk inside. We're just getting half of 1. And so this is often called the Rindler decomposition of ADS. So we heard lots last week about the Rindler decomposition from Ahmed and Tom and Edward and who else. And here, this is the ADS version. So this is like the right Rindler wedge, and then there's we can reflect it over here to a left Rindler wedge, and then there's some region up here and down there that are sort of in the future and the past. And then the point is that we can do the same thing that we did here. So we can look for a set of modes. So here we had these modes e to the ikx times psi k of z, which were a complete basis for solutions of the wave equation in the Poincare patch, for normalizable solutions of the wave equation. So here we can do the same thing. So there's a set of modes which are now labeled by a frequency and an eigenvalue of the Laplacian on the hyperbolic plane. And what they look like is e to the minus I omega tau. So you see we still have time translation symmetry here. It's the Rindler time translation symmetry. Then we have what I'll call a hyperbolic spherical harmonic. I hope nobody is unhappy with that. So it's eigenfunction of the Laplacian on the hyperbolic plane with a plane with eigenvalue lambda, yeah, maybe minus lambda. And then there will be some radial wave function depending on omega and lambda, which is a function of rho. Okay, and again, this will give a complete set of modes to represent fields in the bulk. And then we can just do exactly the same thing. So we'll see that phi of y, where now I'll use y to denote just a bulk point. I won't, so it's not one of the, it's the set of all these coordinates. And this is restricted to y inside of this Rindler wedge. Will be some integral over the boundary of the Rindler wedge, intersect the boundary of ADS. So maybe I'll call this big Y. And then there will be one of these smearing functions, k of little y, big Y, O of y. Just by the same manipulations that we did before. But you see, now it's interesting because before, we had on the boundary this whole domain of dependence of the bulk time slice. But now with this Rindler reconstruction, we have something different. We have the domain of dependence of just half of the boundary time slice. So then we can represent this operator, at least if it's inside of this Rindler wedge, using CFT operators, which are, even if we evolve them down to t = 0 and make them really non-local, they're not that non-local. They still won't spread to more than just an operator which has support on this half of the boundary time slice. Now, let me immediately note that this can be generalized to regions other than half of the boundary time slice by doing a conformal transformation. So here, of course, the boundary time slice just looks like a half interval because the hyperbolic one space is just a line, so that's kind of boring. But in higher dimensions, this will be a ball. It will be a hemisphere of the full time slice at t = 0. And by doing conformal transformations, I can get a similar representation for any boundary region which has the shape of a ball, the shape of a round ball. So in particular, we could have a small region over here. That's very small, sorry, but I guess that's kind of the idea. Or we could have some huge region over here. And as long as this piece of the boundary time slice is a ball, we can have the same kind of representation of the operator. OK, I guess now I've reached this awful point where I have to move all the boards around. Let me see, OK. Maybe I don't have to do it all at once. Okay. Okay. Now, there's a so here, of course, we've still just been discussing the vacuum. There's a non-trivial generalization of this idea of the Rindler wedge to spacetimes which are only asymptotically ADS. And remember that one of the hallmarks of saying something non-trivial in this business is that you're saying things which also work when the spacetime is only asymptotically ADS. So the idea is that each of the, in particular in the case of these ball-shaped regions, there's a way I can describe this wedge. It's called the causal wedge of R. So R, again, was this piece of the boundary time slice. So here in this picture, it was just the hemisphere. In the more general ball-shaped regions, it was still just that ball-shaped region. The idea is that in the bulk, we define the causal wedge of any spatial boundary region. So here, this is a spatial boundary region. Oh, is this a bad color? I think it's kind of bad color. Let me try this. So the causal wedge is defined as the intersection in the bulk of the future of the domain of dependence of R in the boundary, intersected with the past in the bulk of the boundary domain of dependence of R. And so maybe just to be very explicit, I'll put boundary symbols on the domains of dependence so that we're clear that they're boundary domains of dependence. So if you think about what that looks like over here, well, this boundary domain of dependence is just this diamond here that sits on top of the region. And then its future in the bulk is kind of something that's going up like that. And its past in the bulk is kind of something that's going like that. And so indeed, their intersection will be this Rindler wedge. But this is something that we can define more generally. And moreover, it's kind of so if you wanted to extend this idea of representing bulk operators by solving the PDEs, then this is kind of the natural region that you would guess would be the region where this business of solving the PDEs would lead you to a good representation of the operator in the CFT. And the basic reason for that is that if you have a point in the bulk which is not in the causal wedge of R, then, well, it can either send to or receive from signals. Well, it can send a signal which doesn't get into D of R, or it can receive a signal from something that wasn't in D of R. And that would be kind of surprising if you could determine the solution just given boundary data in D of R. At least if you think that information sort of propagates causally in the bulk. And that's the advantage of this definition, is that it's defined purely causally, just using the causal structure of the space. Okay. Moreover, you can kind of give a positive argument that you should be able to reconstruct in the causal wedge, because you can say, if I have a bulk point that's both in the future and the past of the domain of dependence, then I can just send a mission, right? Like I can, somewhere early in the domain of dependence, I can create a little spaceship that flies into the bulk to this point in the causal wedge and then asks what's going on. And then when it's done, it sort of flies back, and it has time to do that and still make it into the domain of dependence. So actually, in some sense, it would be quite surprising if you couldn't reconstruct everything in the causal wedge in terms of the boundary stuff, just using simple causal evolution. Okay. Now, proving actually that in a general asymptotically ADS spacetime you can reconstruct the causal wedge has not been done. It's kind of a hard problem in PDEs, because the boundary value problem that we're solving here is a bad boundary value problem. Now, for the life of me, I can never remember whether it's elliptic or hyperbolic that's bad, but whichever one of those it is, it's bad. Because time is going this way, but we're solving the equation this way. And PDEs don't usually like that. Here we were able to do it using the symmetry of the space. And somehow ADS CFT seems to be telling us that we should be able to do it even not using the symmetry of the space. But you would need someone who actually knows something about PDEs, unlike myself, to show that. Okay. Now, that's basically all I wanted to say about this bulk reconstruction. Just the last comment I want to make is that actually we can do better. So what we'll find in the end is that we're actually, by a totally different method, going to prove that the CFT in the domain of dependence of R actually does know about everything in the causal wedge, and moreover, it knows more. But we're not going to do it using PDEs. We're going to use it using quantum information theory. And so most of the rest of these lectures is going to be explained to you how we do that. And by the way, if you like, that's a prediction for the PDEs. So since we know using other methods it's true, maybe the mathematicians can try and prove it. Okay. So any questions about these things? Questions are good. Ah, yeah. With practice comes ability. Yeah.
Do you expect that with PDEs you can prove it also for the entanglement wedge?
Sorry, what?
Do you expect that with the PDEs we can prove it also for the entanglement wedge?
No, absolutely not. So the entanglement wedge uses additional structure of the correspondence beyond just solving the equations of motion. And you have to say, in some sense, it would really be a pity if all there was to ADS CFT was solving the bulk's equations of motion sideways, right? If that's what quantum gravity is, maybe we should go work on big data or something. I don't know. Yeah. So clearly somehow gravity and black holes has to be important or something, right? And so the entanglement wedge is going to get at that. Yeah.
Can the bulk be present in two different causal regions?
Oh, absolutely. And we're gonna milk that to no end. Absolutely, yeah, just hold that thought. Yeah. Okay, yeah?
The point in the causal wedge of some region can be influenced by some point that is not in the causal wedge, or some point on the boundary that is outside that region. Any of the statement?
Yeah, that's true, but somehow the idea is that that ends up in the initial data here. But that does lead to an important subtlety, which I kind of swept under the rug. And actually, in fact, here I swept it under the blackboard. So this k hat here is actually not a function. I made it look like a function, but it's not. It's a very delicate distributional object. And it only makes sense when the thing you integrate it against is actually a CFT operator. And that's another one of those things for the mathematicians to sort out. I think that's a kind of distribution they don't usually think about. But ADS-CFT somehow tells us it makes sense. And you can check by doing calculations that it does. Yeah.
So the way you have presented it, most of it seems too special to the ADS. Can you make a comment on how some of these things will generalize to other space-time?
Sorry, you mean like that aren't even asymptotically ADS?
Yeah, not even asymptotically ADS.
Oh, ask me at the end of the lectures. Yeah, I don't know. That's a question that you can solve that one in homework problem. Yeah. Okay. Good. So yeah, indeed. Let me emphasize again, like somehow, this business of solving the radial equations, right? We could also do that in quantum field theory in anti-de Sitter space, right? There's nothing to stop us from just forgetting about the graviton entirely and just have phi to the 4 theory, and we can construct a representation of phi in the quantum field theory here in terms of some non-local combination of phi at the boundary. But I mean, come on, right? Like holography is not supposed to be something that applies for quantum field theory in anti-de Sitter space. So somehow the real meat of holography is that these boundary representations, these O's, are actually the local operators of some conformal field theory. And that wouldn't be true if we just took our favorite quantum field theory in ADS and started playing these games. So the real meat of holography is that there's an independent notion of locality, which is boundary locality, which somehow, at least at first, seems like it's going to be a little bit hard to combine with locality in the bulk. I mean, that's kind of right. That's the crazy thing about holography, is that you have the same theory, and it's local in 2 different space-time dimensions, right? It seems like it should be impossible. So yeah, now I'm going to try to formalize a bit this intuition that it's weird to be local in 2 different space-time dimensions at the same time. So we can phrase it by saying that there's a problem that ADS-CFT needs to solve. And the problem that it needs to solve is radial locality. So what ADS-CFT needs to be able to do is we can have a time slice of the bulk like this, and we can have some operator, phi of little y, sitting here in the center. And then out here, we have some local operator O of big Y sitting in the CFT. And well, from the bulk point of view, these 2 operators are space-like separated. They're space-like separated in the radial direction. So you might think that, therefore, this should imply that the commutator of phi of little y with O of big of Y is equal to 0. That's certainly what it would have implied in quantum field theory, right? If you take good quantum field theory class, on day 1 you learn that operators commute at space-like separation. So here, it looks like we have some operators at space-like separation in the bulk, so maybe they should commute. But that's a little bit surprising from the point of view of the boundary conformal field theory, because in quantum field theory, what we usually think is that if I give you the set of all the local operators on a fixed time slice, that generates all of the other operators. So for example, in a spin chain, if you have 10 spins in a chain, then it's a standard fact that all the operators in the Hilbert space are generated by sums of products of the single site Pauli operators. So in particular, if you commute with all the single site Pauli operators, you commute with everything. And then by Schur's lemma, you're just proportional to the identity, okay? So this seems to be asking this operator in the bulk to do something rather challenging, because it's asking for it to both be non-trivial and to commute with all the operators in the boundary at a fixed time, all the local operators in the boundary in a fixed time. In fact, there's kind of in mathematical quantum field theory, there's kind of an axiom, which is called the Timeslice Axiom. Yeah, one sec, which says that any bounded local operator which commutes with all of the operators with support in an open set of a Cauchy slice has to be the identity. And again, it's just this idea that the local operators on a time slice generate everything. Yes?
And so we should remember addressing that?
Yeah, so this is one of those things where I have to slightly improve the argument to deal with the dressing. So I'll just say it in words to make you happy. So if I needed to dress that operator, I can dress it with a gravitational Wilson line that goes to a single point on the boundary. Then I would conclude that I have an operator which commutes with all the boundary operators except at that point, okay? But by a similar axiom in quantum field theory, if you commute with all the local operators everywhere except at one point in space, then you yourself are a local operator at that point. But this guy can't be a local operator at that point because it's not consistent with bulk causality. Yeah?
To reach that conclusion, you're using the notion of being space-like separated in the bulk.
Yeah.
Do you need to reconstruct that in the CFT too?
Well, here, so I'm not yet saying we can get this. I'm saying that you might want this. You know, at least if you think about what do you want, this might be a thing you want, and we're seeing that you can't get this. So then we have to revise our hopes and see if there's something else which is all we really need. Yeah. Yeah.
What does the statement about bulk dressing change if we want to think past perturbation theory and the IR effective field theory?
Well, past perturbation theory, it's not really clear what we mean by the gravitational path integral. So everything I say, including my definition up there, is going to be is defined to all orders in gravitational perturbation theory, which incidentally is enough to talk about different backgrounds because you can sort of resum series of Feynman diagrams to change the background. But what you can't do is include things like, scattering, two electrons together at 10 times the Planck scale with 0 impact parameter and asking what happens. Yeah. Okay. All right. Now, so this issue of radial commutativity, of somehow needing to commute with all the local operators in the boundary, has an interesting interplay with this Rindler reconstruction that we were talking about before. Because, well, let's again draw this time slice now from above. So here's our phi of y sitting here. So now let's pick a local operator. So I don't know, how about this one right here? Here's a boundary local operator, O of y. Well, we just learned that if this operator is in this causal wedge of a boundary region, then I can represent it in the CFT only with support in the boundary of that causal wedge. And so in particular, I can take my boundary region to be like this, where I go the long way around. And then so the causal wedge is like that, and it clearly contains this point. But then in the boundary, then this guy has a representation just here, which in the boundary theory is space-like separated from our local operator, and therefore commutes with it. And here, not even commutes with it up to e to minus 1 over g, but really commutes with it, because they're space-like separated in the boundary CFT. And then you might say, okay, well, okay, fine, that's true for that operator, but I changed my mind, I meant a different operator. Let's say I changed my mind and now I meant this operator up here, O of y prime. Well, that's okay. I can just now change my region. So here's my r prime. And I can go around this way. And now the causal wedge is like this. And this guy is still in the causal wedge. That's the question that was asked before. But now, so I have a representation over here. And that one, well, again, it exactly commutes with my O of y sitting there. Okay? So again, I have a representation of the same bulk field where it computes exactly with this one. And let me remind you that these different representations, that we got by moving the Poincare patch or which Rindler thing we meant, from the bulk point of view, they're all just Bogolubov transformations. So it's supposed to be the same operator. It's not a different operator. You're just representing it using different modes. But somehow here we're saying that there's going to be some representation. There's always some representation that commutes with any local operator we want. And so if all those representations are equal, then again we're in the soup with the Timeslice axiom. So then we've again find ourselves in this unenviable task of wanting an operator that commutes with all the local operators but isn't proportional to the identity. Yes?
Sorry, now what if the version operator is constituted at the center, like closer to the boundary?
So if it's what?
If it is closer to the boundary.
Well, we can consider other setups. This one is enough to get us in trouble, so. Yeah. I mean, if you want, I can do a conformal transformation and move this over there, and there'll be some other paradox in that conformal frame, but I'm happy with this one.
I thought the aim was to construct a bulk using the boundary
Yeah.
information.
Yeah. But remember, in the end, all the operators we talk about are in the CFT. Because remember, we had this isomorphism. And so my rule is that I just talk about everything in the CFT. So the bulk operators is represented in the CFT as an operator. And then so then it has to obey the axioms of operators in the Hilbert space of the CFT. OK. So that's kind of fun. Let's see. Now I need to. Well, maybe I'm going to. Yeah, let me repurpose this board up here, because I just want to draw one more picture, and then we're going to change gears. This board doesn't have much on it. OK, so we can make things even crazier. And so here's the picture that I'm contractually obliged to draw in every talk that I give. So we can imagine splitting the boundary into 3 regions, R1, R2, and R3. So then we can draw the Rindler wedges of these guys, or the causal wedges, like that. Here again, I'm always talking about just on a spatial slice. And we can imagine, again, some operator 5y sitting in the center here. So now the funny thing about this operator is that it's not in the causal wedge of any one of the regions, but it is in the causal wedge of any 2. So in particular, there's a representation of this on R1 and R2, or on R2 and R3, or on R1 and R3. So somehow no one region knows about it, but any 2 regions do know about it. And this is, again, just to me, it was very surprising. So actually, Ahmed came to me with this question in Aspen, I guess 4 years ago now. And it was really struck me. It just seems like a crazy situation. So somehow we think in quantum field theory, operators should have the decency to know where they're localized. When Douglas talks about the operator growing, right, he's implicitly assuming that the support of the operator is a well-defined thing. And he's not wrong. In quantum field theory, the support of the operator is a well-defined thing. But here, somehow, it seems that ADS-CFT is telling us that actually it isn't. It's somehow more malleable. That sometimes you can think about it like this, but you also might want to think about it like that. So somehow, by all of these issues are coming from trying to harmonize locality in the bulk with locality in the boundary. Now, before I go on to explain the solution, let me just make a comment. So for me, at least, all of these paradoxes were motivated by trying to find a simpler version of the kind of paradoxes that Ahmed was talking about in his lectures. Ahmed's paradoxes, they all started with, here's something that we think is true in low-energy effective field theory, like the creation operator behind the horizon, lowers the energy, or something like, that these modes should be entangled. And then taking these effective field theory facts and downloading them into the Hilbert space of the microscopic theory of quantum gravity and getting in trouble. And here we're kind of doing the same thing. We're taking commutativity at space-like separation and trying to put that into the CFT, and then we're getting confused. Okay. So now, fortunately for us, these ones turn out to be easier to resolve than Ahmed's. I will be able to resolve them for you, whereas I can't yet resolve Ahmed's, but I think it's sort of on the right track. Okay. So I go another 20 minutes, right? Yeah. Okay. Okay, so that's it for the sort of bulk side of the story. Now we're going to talk about ADS-CFT, and now about quantum error correction, and now I have to do a racing party. So talk amongst yourselves. Okay. All right. Uh-oh. Now when I put it back, it's going to be like what happened for Douglas. Let me. Okay. Seems good. All right. So now I'm going to talk about quantum error correction. So this is going to be the new tools, which then we can use to get ourselves out of the confusion that we just got ourselves into. So the basic idea of any error correcting code, quantum or classical, is that if I want to send you a message and I'm worried that the message might get polluted along the way, either it might just run into some obstacle, or even some adversary may come in and intentionally try to change the message. So if I want to avoid that, the idea is that I use redundancy. So if I want to send you a bit I, oh god, yeah, now it is exactly like Douglas. Okay, let me see. I shouldn't make it sound like it's Douglas's fault. If you're here, Douglas, it's not your fault. In classical error correction, I want to send you a bit, I, it could be 0 or 1. So one thing I can do instead of sending you the bit is I can send you 3 bits, which are all in the same state. So this is called the repetition code. And then the idea is that, well, if somebody comes along and switches one of the bits, or we lose one of the bits, either way, whichever bits you get, you can just do majority vote. And at least there will be some limited set of errors which you can correct. Now, if somebody comes along and flips 2 of the bits, you're out of luck. So any error correcting code, its protection ability is limited. Now, quantum mechanically, it might seem like it's going to be impossible to do something like this because of the no cloning theorem. Okay? And indeed, you can check that, well, so I can define a unitary transformation which takes the state I0, 0, 2 zeros, and sends it to the state I. So that's just the same encoding map that we had here. But it's clear that as soon as I act with this unitary on a superposition, so for example, I try to act on that state, what I get is that, which is not 3 copies of the state that I put here, right? It's an entangled state between the three qubits. So somehow if I want to be able to send you a generic quantum state in a redundant way, the repetition code is not going to be how I do it. Now, despite this problem, quantum error correction is possible. And the reason is that although we don't have this kind of redundancy, there's a new kind of redundancy. And the slogan is that what we do is we want to store the information non-locally in the entanglement between many qubits. It sounds fun when you say it that way, but maybe it also sounds opaque if you haven't thought about it before. So as with anything else new, it's always best to start with an example. And so this example also I'm contractually obligated to talk about. So the example is the 3-qubit code. So say I want to send you a state of a qubit. So a qubit is a 3-state qubit. So sum goes from 0 to 2. It's a 0, 1, or 2. Now, if I just send it to you, all sorts of things could happen to it. So the idea is instead of just sending it to you, I take a spin 1 atom and putting it in an envelope and sending you the envelope. What I'm going to do instead is I'll encode it into 3 spin 1 atoms, or more abstractly, 3 qubits, in a way that looks fairly similar. In fact, so far it just looks like I put tildes on top of things. But the important thing is that these I tilde are actually, it's a basis for a 3-dimensional subspace of the 27-dimensional Hilbert space of 3 qubits. And so what the subspace looks like, 0, 0, 0, plus 1, 1, 1, plus 2, 2, 2. There's encoded 1. 0, 1, 2 plus 1, 2, 0 plus 2, 0, 1. And then, well, okay, I guess I'm out of luck. I have to go up here. The encoded 2 is 0, 2, 1 plus 1, 0, 2 plus 2, 1, 0. Okay. And if that's hard for you to remember, then we can also define it by saying that the encoded I state has algebraic representation. It's k plus I, k plus 2i, k, where the arithmetic is done mod 3. Okay? So this is a sort of more compact representation of these states. And so this is so these three states are orthogonal. So they span a three-dimensional subspace of the 27-dimensional Hilbert space, and so it's usually called the code subspace. And you see, I send the message by putting it in this code subspace. Now, I want you to note two things about the subspace. So one thing is that it's symmetric under cyclic permutations of the Qubits. That's kind of obvious in this way of writing it. In this way, you have to relabel the sum. And moreover, these states are very entangled. So none of these states is even close to being a product state. So actually, I want to. That's not. Well, okay. That one's too heavy, especially without enough lead-in. Okay, now the claim to fame of this code is that it has an encoding map which acts only on the first two Qubits. So by that, I mean that the encoded state I can be represented as U12 tensor I on the third Qubit. And so this will be the only time I write a tensor I in this talk. From now on, when I write U12, I mean it acts on the first two Qubits, but it might be part of the bigger Hilbert space. So I once gave a talk where I didn't write this in front of Greg Moore, big mistake. I don't know if Greg is here, but okay, so these states can be represented like this, where this chi state is some maximally mixed state on two Qubits. Okay, and if you want, you can check, it's pretty easy, that acting on ui and k, this u12 just sends it to k plus I, k plus 2i. Okay, if you look at the representation up there, that's kind of obvious. So this is what the unitary is. Now,
what is I in your first equation?
Here?
There's no really intersection.
So in this,
What's that I on that?
there's an I on the left. I'm sorry. Yeah, it's there's an I on the left. Yeah, sorry. Okay. So why is this interesting? Well, the reason is because say now I in the mail send you 3 envelopes containing 3 spin 1 particles, which are in the encoded psi state, which I can represent by acting with U12 on the unencoded psi state on the first Qubit times chi on the second 2. Okay? So any arbitrary state here I can prepare by just sticking in the psi I want with these coefficients on the first Qubit and then acting with this U12. Which, by the way, shows that there's no issue with cloning to prepare a state in the subspace, right? There's a unitary that does it. Well, now say that the third Qubit gets lost, or the third envelope, falls out of the plane or something on the way from me to you. Well, that's okay, because you can, as long as you receive the first 2 of the Qubits, you can just take them over to your friend, the experimentalist, and ask them to act on those 2 Qubits with U12 dagger, with their quantum computer that they have in the basement. And if you act with U12 dagger on psi tilde, then sure enough, you just get back psi chi, And well, you don't have the third qubit, so you just have some mixed state of 2, but who cares, because there's the state sitting there in 1. So you recovered the state. And moreover, by the cyclic permutation symmetry, if I can do it on 1 and 2, I can also do it on 2 and 3, or 3 and 1. Okay? So there, for any 2 of the qubits, there will be a unitary, which encodes the circuit, starting from putting the state on just one of the 2 qubits that you have, which has support only on the 2 qubits that you have.
You need to know which one's lost.
What?
You need to know which envelope was lost.
Yeah, that's correct. So the envelopes need to have numbers on them. So technically, so you know which ones you get. And so strictly speaking, we say that we're correcting the erasure channel here instead of the depolarizing channel, which is the one where you don't know which ones you lose. Yeah. Okay. So that means that actually we can recover the state on any 2 of the qubits. Okay. And so that should sound sort of familiar to what was going on up there. Get rid of that Bessel function. Ugh. Okay. Okay. Now, so indeed, so this is starting to sound like what we had up there, but it's not quite the same, because here I'm talking about recovering an arbitrary state. Oh, sorry. Yes.
If I have a CFT on the sphere and a finite subregion, how do I quantify the maximum amount of error correctable?
Well, you're getting way ahead of me. Let me just talk about 3 qubits. We can try to do continuum quantum field theory later, tomorrow, I guess. Okay. So here we were recovering states, but there we were talking about operators, right? Because we were trying to come up with a CFT representation of an operator in the bulk in terms of an operator in the Hilbert space of the CFT. So the idea is that we can introduce this notion of logical operators. So a logical operator is one where if we act on the code space, we get just some matrix element, Ji, acting within the code subspace. So it's an operator that implements some transformation within the code subspace, and then we don't care what it does on the states that aren't in the code subspace. But we do care that it's true both for that operator and its Hermitian conjugate. So this will be O dagger Ji J tilde. So for any operator on the 1 qubit Hilbert space, we can lift it to an operator on the 3 qubit Hilbert space, which acts in the way that we want on this particular subspace. That's no challenge, right? We are just, we have a 27 by 27 matrix, and we're picking 9 of the components. More, actually, I think. Well, yeah, anyways, because we want both of these conditions. But usually when we do this, the O tilde operator is going to be an operator that has support on all 3 of the physical qubits. Yeah. So maybe this language. Let me define these terms explicitly. So the logical qubit is the encoded one in the code subspace. There's 1 logical qubit, and we say it's encoded into 3 physical qubits, which are the 3 atoms that we put in the envelopes. Okay. So usually we think that an arbitrary logical operator needs to have support on all of the physical qubits in order to work, right? Like if we just pick some stupid subspace, that would be true. But we didn't pick a stupid subspace, we picked a good subspace. And so there's a little trick we can play. We can just, for example, we can define O12 to be just U12, what I'll call O1, U12 dagger. And so this is an operator which, well, let's look at what it does. So it takes the state like this. It decodes with U12 dagger so that the code subspace is now just sitting on the first qubit. Then it acts with whatever operator we want to be acting with, whatever logical operator on that first qubit, and then it re-encodes with U12. And so indeed, this is an operator which obeys these rules. So for any logical operator on the code subspace, we can represent it just on the first two qubits, because you see there's 1, 2, and 1, and 1, 2. So all these operators just have support on the first two qubits. And moreover, by symmetry, I can also have a O23 or O13, where I put a U23 and a U13 here instead of a U12. Yeah?
Sorry, is there a finite number of operators that I can act on these three qubit states?
Well, I'm not sure how you're counting operators. There's a finite basis for this set of operators. There are, of course, infinitely many linear operators, even on a finite dimensional Hilbert space.
Yeah, I would need to qualify some of these operators that they do cause some errors.
Well, no, here I'm talking about logical operators. So logical operators are not errors. Logical operators act within the code subspace. So if we were using this to do quantum computation, logical operators would be the steps of Shor's algorithm, right? They would be the things you want to do to the system in the process of doing your computation. Here for us, they're sort of, well, eventually they're going to be like the bulk effective field theory operators, but we'll explain that in a sec.
So I think I wasn't clear. I want to keep the logical qubit, one of those qubits, but look at all the other operators which will...
Clearly most operators will not preserve the code subspace, right? So we're talking about a special set of operators here. Yes, there are lots of other operators. Okay, now let me just make two other comments and then I'll be done. So the first comment is that we had this state chi here, which was maximally entangled, and that's actually important. Okay, it might not be obvious, but actually it's obvious, so let me say why. So say that chi had instead been a product state. Okay? Had chi been a product state, then the encoded state, psi tilde, or let me call it I tilde, would have been equal to some state just on the first two qubits, tensored with some state chi, sorry, 1 and 2, on the third one. And in this situation, the information is just in the first two qubits. So in particular, if you can't access it from just the first qubit, you're never going to be able to access it from both the first and the third because this is useless. Right? It just is no useful information. So the fact that we can simultaneously get this to work for 1 and 2 and 1 and 3, but not 1, requires this chi to be entangled. Okay? And you can actually try to put bounds on how entangled it needs to be. It's something I think it needs to be explored more. I think some of the Berkeley people were working on it at some point. Okay, and then the final comment, and then we'll be done, is I want to now go back and say what this has to do with holography. So that's all I was going to say about the 3-qubit code purely as a code. Let's now try to interpret it as a theory of quantum gravity, because that would be fun. So the basic idea, so now to make a model of holography, we say that the three physical qubits are the local CFT, degrees of freedom, and the one logical qubit is a bulk effective field theory degree of freedom. And so in this theory, both of them are very simple. So here's our circle. And so we can imagine, let's put the qubits here, 1, 2, and 3. So the full 27-dimensional Hilbert space is the Hilbert space of the boundary CFT. Then the bulk qubit, the logical qubit, is sitting here in the center of the bulk. And then you see what this whole discussion tells us is precisely that if we have a bulk operator acting here, then we can represent it on any two of the boundary regions, on the union of any two of the boundary sites, but not on any one of the boundary sites, which is precisely what we saw from the ADS Rindler reconstruction. And moreover, and this will be the last board here, and then we can all go to lunch. Moreover, if we look at the commutator, we can ask, what does this say about this radial commutativity puzzle that we had before? And so we can look at the matrix elements between two code subspace states of an arbitrary logical operator with an operator with support on only one of the boundary sites, so say on the third one. So this is like a CFT local operator. It's an operator that acts just on one of the boundary lattice sites, okay? We can look at its matrix element in the code subspace of its commutator with this guy in the center. But sure enough, this guy is always acting to the left or to the right in the code subspace, which means by this equation, I can replace this with O12, but then that commutes with x3, and so this is 0. And moreover, had you put x2 or x1 here, I could have just picked one of the other representations, and either way, I would have gotten a representation that commuted. That's what I was saying about over there on the bottom blackboard with the Rindler. But you see here, somehow we're doing this with the O tilde being non-trivial, okay? And the reason is precisely because we're not showing that this commutator is 0 as an operator. We're showing that its matrix elements in the code subspace are non-zero. What? Sorry, its matrix are 0. Yes, that's correct, are 0, okay. All right, so that's good. Last comment, but I mean, then you can say, okay, come on, but then what about all the other states, right? You told us, you know, well, I guess I erased it now, but you told us that the correspondence is an isomorphism and that every state in the boundary has a bulk interpretation and vice versa, okay. So fine, this shows that you can solve radial commutativity within the code subspace, but what's the bulk interpretation of all the other boundary states, right? Until I can tell you that, I haven't told you anything, okay. And so here's the claim, and today it's just going to look like kind of a bold claim, and then hopefully tomorrow it'll become more plausible. The claim is that in the orthogonal complement of the code subspace, what's going on in the bulk is we just have a big black hole here, which is Eden our point, and it has a 24-dimensional Hilbert space of microstates. And so somehow the physics is, you know, that's where the gravity comes in. Somehow it's the thing that tells us that maybe actually we should have only asked for this commutator to be 0 in the states where there wasn't this huge black hole here. Whereas had we had quantum field theory in the bulk, then we really would have needed this to be 0 as an operator. Okay, I think I'll stop there.